Hey everyone, my name is Kyle Shevlin and welcome to my introductory course on functional programming in JavaScript, where we'll learn just enough of the concepts in order to start doing functional programming today. One of the goals of this course is to introduce as little jargon as necessary. Functional programming vernacular can be very intimidating and frankly, a barrier to entry, so let's break down those barriers and we'll avoid it whenever possible. Another goal of this course is to teach you functional programming in a language agnostic way. Sure, the course is written in JavaScript, but you can take these concepts and apply them equally as well to Haskell, Scala, Clojure, ReasonML, really any functional programming language. Together, we're going to learn about higher order functions, pure and impure functions, immutable data structures, currying, partial application, the importance of argument order in our functions, point-free programming, composition, a tiny little bit of math theory with the associative property, and how to debug our compositions. My personal hope is to inspire you to take what you learn here and go explore functional programming even more. Thanks. A higher order function is any function that does at least one of the following two things and oftentimes does both. First, it accepts a function as an argument. And second, it might return a new function. To demonstrate this, we're going to create a withCount higher order function. WithCount will take a function as an argument, and what it will do is return a console log of how many times we've called our newly returned function from within it. To do this, we'll store a count variable, and we'll return a new function that uses the rest operator to gather up the arguments passed to it. And inside the body of our return function, we'll log out the count while also incrementing it. And we'll return the result of the function that's been called with the spread arguments. Now that we have our withCount higher order function, let's create a simple add function to use and pass into it. It'll receive x and y as arguments and return their summation. We can now create a counted add function by using our withCount function and passing add to it. Now let's log out several uses of counted add. I'll modify some of the arguments. If we save this and print it out in the terminal, we should see a call count with each one. Mutable data structures can be changed after creations, and immutable ones cannot. Mutations can be thought of as side effects in our applications. I'm going to demonstrate this through the use of an array. Let's create an array A. We'll equal it to a few values. We're going to assign a variable B to A. What this does is create a new variable with the same reference as A. We can see this by using a strictly equals equality check because it will check the references are the same, not that the values are the same. Now, if I make an update to B by pushing a value onto it, if I log out A, we'll see that A has been updated as well. This is because A and B are not different arrays. They're a reference to the very same array, and when we make changes to one, we actually make changes to the other. This can be problematic in our code. Functionality that's operating on B would change A even if we didn't intend to do that. The same holds true for objects. If I create an object of A, we'll give it a property foo, and we'll set it to bar. If I assign that reference to another variable B, and I make changes to B, such as reassigning foo to baz, if I log out a.foo, we'll see that it's been updated. This is problematic for functional programming because it breaks the purity of our functions. When we make updates to data, we want to return brand new data structures that contain all the elements of the previous state of the data structure plus our updates. For instance, push is a mutation on an array. As you saw, it changes all references to that same array. However, we could create an immutable push function. It'll receive a value and an array, and will return a brand new array by using the spread operator to create a clone and then push the value onto that. If we create an array again of 1, 2, and 3, this time if I make a second array by pushing a value onto it using our new function, we'll push 4 and we'll use A. We'll see that A hasn't been updated And we'll also see that A and B do not equal because they are references to different arrays. We can create similar functionalities to handle changes to objects and so forth. One metaphor I like to use to describe this to people is the metaphor of taking a drink from a glass. I'm going to create two classes, a mutable glass and an immutable glass, and we'll make a take drink method on both of them and show the difference between handling it mutably and immutably. We'll start with the mutable glass. We'll have a constructor that takes a content and an amount and assigns this dot content to content and this dot amount to amount. And then we'll create a take drink method that will take a value. And what we will do is we'll update this dot amount directly and we'll return this instance of the glass. So this dot amount equals math.max. We're going to use this to guarantee that we never get less than 0 amount in our instance, since we can't drink what's not there. And then we'll return this. If we create a glass, we'll call it mg1 equals new mutable glass. We'll give it a content of water and an amount of 100. Now, if we store the value returned to us after taking a drink, we can see that they are the same instance through a strictly equals comparison, and see that both mg1's amount and mg2's amount is the same, which makes sense since they're the same instance. And we'll log this out in our terminal, and we get true in each case. That's because we handle it mutably. We change the value directly, and we've changed the data structure after its creation. I'm going to comment these out so that they don't turn up the next time I run the terminal. But now we'll create an immutable glass. The constructor will look exactly the same with content and an amount. This dot content equals content. This dot amount equals amount. And we'll make a take drink method that also takes a value. But here's where a big change occurs. When we take a drink, rather than returning back the same glass that I had before, I'm going to return a brand new glass with brand new content in the correct amount. To do this, we simply create a new immutable glass from within. We pass the content on again because it should stay the same. We didn't turn water into wine or anything like that. And then for the amount, we'll do the same calculation. This dot amount minus the value, and the lowest it can be is 0. But because we return a whole new glass, we should see that when we create glasses, when we make updates, their instances are no longer the same. So we'll create an ig1 variable that's a new immutable glass, and we'll also make it water, and we'll give it 100. And then if we store the glass returned to us after we take a drink from ig1, take drink, we'll do 20. What we should see is that when we compare ig1 and ig2, they aren't the same instance anymore. We can do that doing a strictly equals comparison. That should be false. And we should see that the amount of ig1 hasn't changed and thus does not equal the value in ig2. Both of these should be false. Currying is the act of taking a function that normally receives more than one argument, such as add, and refactoring it so that it becomes a higher order function that returns a series of functions, each accepting only one argument and only evaluating once we receive our final argument. If I try using add function the normal way by passing both variables in at the same time, and I log that out, all I'll get back is a function. This happens because the second variable is ignored, and we receive back the function that's been returned on line 4. Instead, I can save the return function as a new variable. In this case, we'll call it add3. I can now take our new function and give it its final argument, and I can reuse this function. I'll call it several times with different numbers. And if I log this out, I get the correct summation. Every function in functional programming is curried like this. We can write our curried functions much more succinctly using an ES 2015 arrow function. Arrow functions implicitly return each expression that comes after an arrow. In this case, we return this full function after receiving our x, and after receiving our y, we return the evaluation of x plus y. At this point, I want to briefly discuss some jargon, that is the word arity. Arity describes the number of arguments a function receives. Depending on the number it receives, there are specific words to describe these functions. A function that receives 1 is called a unary function. A function that receives 2 arguments is called a binary. 3 equals a ternary, and 4 equals a quaternary, so forth and so on. Thus, the act of currying can be described as taking a multivariate function and turning it into a series of unary functions. A pure function is a function that derives its output solely from its inputs and causes no side effects in the application or outside world. The most common pure functions people have encountered are mathematical functions. You might recall seeing a function that looks something like this. This is a function that receives one value, x, and derives its output from that value, in this case, x plus 1. We can write this in JavaScript as this. It's pretty easy to reason that this is a pure function. We get the same output given the same input, and there's no outside world for us to cause a side effect in. To understand this further, let's compare this with several impure functions. The first impure function we're going to make is one whose output is not solely derived from its inputs. For example, let's consider you're making a cart total function, and for one reason or another, you've decided that one of the prices needs to be a global constant. Our cart total function takes a quantity and multiplies that against this constant. On the surface, this will seem like a pure function because we always get the same output based on the same input. We can see this by calling it multiple times with the same value and logging it out to the terminal. In both cases, we get 38. While we're getting the same result, this is an impure function because the state of our application has an effect on the output of our function. We can see this by changing the value of cost of item and outputting that to the terminal. I'm going to comment these out so they don't continue to log out in the terminal throughout the rest of the exercise. Our second example of an impure function is one that gets the same input and gives us different outputs. Oftentimes in our applications, we'll need to create objects that have unique identifiers, such as IDs. So let's create a generateID function. This function will return several integers randomly. We can see that this itself is an impure function. We can call it several times and we'll get a different result each time. Now let's use our impure generateID function inside of a factory function to create user objects for us. To create a user, we'll take a name and an age and we'll return an object with an ID using the generateID function to create it, and just return the name and age. Let's call this several times, giving it the same inputs. In this case, I'll use my own name, Kyle, and my own age, 33. We'll save it and print it to the terminal, and we'll see that we get similar objects, but they're not the same. The ID is different in each one. The impurity of the generateID function makes our factory function impure as well. The way to fix this is to move the impure function outside of the factory and call it somewhere where we're expecting the side effect to happen, and then pass the ID as a parameter into our create user factory. Again, I'm going to comment out this code so we don't see it repeated in the terminal as the lesson continues. Our third example is a function that creates a side effect within our application. Similar to our global state example, we can create functions that mutate the state of our application, thus causing a side effect. Let's say we're keeping track of a mutable value, in this case ID, in our application. If we then create a function that mutates this value, we have an impure function. Let's say, for example, you're creating an application that involves food items, and we make a factory function called createFoodItem. If we generate our ID for that object by mutating the global ID value, this is an impure function. We can call this function, and we'll do it several times with different food items, and we'll see that the ID increments like we expect, but if we also log out the ID value itself, it has been mutated and is a different value. Once more, commenting out these logs so that they don't continue to show up in the terminal throughout the lesson. Let's make our final impure function example, and that would be a side effect of the outside world. Believe it or not, I've been using an impure function this entire time to teach you this concept. Console.log is an impure function because it creates a side effect in the outside world. Every time I use console.log, it affects the terminal, and that's a side effect. So if I have any function that uses console.log in it, such as a logger function that takes a message and outputs it, that's an impure function as well, even if it's just a nice message to say, "Hi, eggheads." Partial application occurs whenever a curried function has some but not all of its functions applied. To demonstrate this, we'll create a curried getFromAPI function. It'll receive a base URL, an endpoint, and a callback to be called once we've received our data from the request. We'll use node fetch to fetch our data. Our URL will be a combination of the base URL and the endpoint. We'll turn our response into JSON. After that, we'll call our callback on our data, and we'll catch any errors for good measure. Now let's partially apply a base URL. One public API we can use is the GitHub API. Now we have a partially applied getGithub function that we can pass different endpoints to. Let's create functions to the user's endpoint and the repository's endpoint. Now we have two new functions, each that have partially applied the same base URL but have partially applied different endpoints. The last thing we can supply to them is a callback, which will trigger the fetch. Let's use the getGithub users function and supply different callbacks to each one. And for the first one, let's log out the user login names. The main benefit of partial application is our ability to delay the evaluation of a function while still supplying some of the arguments to be stored and reused throughout our application. For the second one, let's log out the user avatar URLs. You can see we have avatar URLs and we have usernames. Often when we pass functions as arguments into other functions or methods, we use anonymous functions with interim variables. If we consider the map method, you might see something like this in order to double the numbers of our array. While this works, this actually leaves us a lot of surface area for bugs and misunderstanding. X acts as an interim variable. It is a placeholder for our data. We can just as easily name it foo, bar, or y. None of those tell us much about what the data is or even what we are doing to the data. Point-free programming is when we remove those anonymous functions and interim variables and instead pass in named functions directly into other functions. This works by pulling the anonymous function out and making a named function with it. In this case, we'll make a double function that receives any value and returns its double. And then we can pass double directly into array. What we gain from point-free programming is legibility. It's really easy to read map and double and know that each item is being doubled. We reduce the surface area for bugs by not introducing new interim variables. And we gain the ability to unit test our named functions. Composition is the heart and soul of functional programming. It's how we build up complexity in our applications. If you recall from math class, you might have seen a function such as this, f that takes an x and returns some formula using x. In this case, we'll use x plus 2. And then you might have seen a second function, we'll call it g, that also takes an x and returns some other formula using that x. In this case, let's do x times 3. Composition is the act of combining these functions so that the output of one becomes the input of the next one. We can see this by nesting them together. We'll start with our function f, we'll nest our function g inside of it, and we'll give it a value. In this case, let's give it the value 5. We'll log this out to the terminal and see the result. We got 17, which makes sense. 5 times 3 is 15. 15 is the input into our f function. 15 plus 2 is 17. Our applications typically don't have functions with single letter names, however. This means that nesting them together to make compositions can be really cumbersome. Let me give you an example. Let's make some curried functions that we can use to make a composition. Let's start with a scream function. It'll take a string and uppercase it. Next, we'll make an exclaim function. That'll take a string and add an exclamation point. Lastly, we'll make a repeat function that'll take a string and double it, adding a space in between. Now we can make a composition similar to the one we made with f and g. In order to make this composition, we have to think from the inside out. The first thing I want to do with my string is scream it. So I'll write the scream function and I'll give it a string. In this case, I'll say I love Egghead, because who doesn't? The next thing I want to do has to wrap that, so I want to exclaim it. Lastly, I love egghead so much I want to repeat it. We log this out to the terminal, we should see how our string was transformed. We see that our original string was uppercased, an exclamation point was added to it, and that exclaimed string was repeated. As you can see, this can get really lengthy and kind of hard to read, especially if we had even more functions. A better way to do this would be to create a higher order function that can accept any number of functions as arguments and create a composition out of them. So let's do that. Our compose function will receive any number of functions as arguments, so we'll use the rest operator. Next, it'll return a function that's awaiting its initial value. We'll call it x. From here, we have an array of functions. Notice that the order that we want to call them in, though, goes from right to left. We first call scream, exclaim, and then repeat. In order to do this, we're going to use the reduce right method. So we take our functions, we use reduce right. Reduce right accepts a accumulating function as its first argument. The arguments to that function are an accumulator and the current item, which is our function. And what we want to return with each iteration is the result of calling the accumulated value on that current function. The second argument to reduce right is our initial value, which is our x. We can now use this function to easily create new compositions. Let's create a with exuberance function that will be a composition of our scream, exclaim, and repeat functions. The order of arguments to our compose function go from right to left. So we need to pass as the first argument the last thing that we want to do, and the last argument as the first thing we want to do. The last thing we want to do is repeat our string, the middle thing we'd like to do is exclaim, and the first thing we'd like to do is scream. Now we can use our with exuberance function to log out our I love egghead string and get the same result. For one final and thorough note, I'd like to add that in certain libraries such as Ramda and Lodash-FP, you might come across another way to make compositions. In those libraries, you'll come across the pipe function, which is the same as compose, but the argument order has been reversed. So pipe also takes any number of functions, an initial value, but this time calls reduce with the same functionality. Thus, to make our with exuberance function with pipe, we just change the order of arguments. While the pipe function exists, it's somewhat more common to see the compose function used in functional languages because it follows the mathematical model of composition. The order of arguments in non-curried functions is somewhat trivial and a matter of preference. If I have a map function that receives an array and a callback and uses it, because I receive all the arguments at the same time, it really doesn't make a difference if I change their order to be callback and array. I need both arguments in order for the function to work, and I can't create partially applied functions. However, if this is a curried function, the order of arguments makes a huge difference. Let's make a curried map function similar to Lodash's map function. We'll first receive an array, and then a callback, and return array.map passing in the callback. If I now create an array and a function to use in the callback, if I create a partially applied function by supplying the array, we can see that while we can pass different callbacks to it and get the right result, we've locked in the data. The only thing we can change is the callback. This doesn't give us any extra utility than we get from just calling the map method directly on the array. If we change the argument order to receive the callback first and then the array second, we derive much more utility from this curried function. Now we can create a with double function that uses the map function and supplies the callback and awaits any array of numbers to double. For example, the array we already have, or perhaps an array of even numbers. A useful way to think about curried functions is to order arguments from most specific to least specific argument. The least specific argument in every case is always going to be the data. That could be our Boolean, a number, a string, an object, or an array, the primitives of your language. Take, for example, a prop function. Prop will be used to derive a value off an object, by receiving a key and then an object and returning the value stored at that key. I can now create partially applied functions that are designed to retrieve values out of any object. In this case, I'll create a prop name function with the specific argument of name. Now let's create a list of people. They'll be objects with name properties. I'm going to use the names of some of my friends. Now I can use my prop name function, which expects its data last, in combination with my map function that expects its data last. If we log this out, we'll see an array of names. Functional compositions obey the associative property of mathematics. Let me demonstrate. In addition and multiplication problems, if there are two or more occurrences of the same operation, then how we group the numbers doesn't matter. If I take the equation 1 plus 2 plus 3, I can group 1 and 2 together and add them to 3, or I can group 2 and 3 together and add them to 1. Each of these equations is equivalent. The same thing occurs with our functional compositions. I'm going to import a compose function and some curried functions to make some compositions with. Just like our math problem before, I can create a composition with scream, exclaim, and repeat. Now I'm going to save a string variable that we can pass into all our compositions. If we log out our first composition, we should see in the terminal, I love egghead, both with exclamation points. Now, the associative property allows us to make sub-compositions within our composition to create the same functionality. We'll start by making a composition of repeat and exclaim. If I then create a composition with repeat excitedly and scream and pass it the same string, I'll get the same result. The other subcomposition we can make is to combine exclaim and scream. We'll call it scream loudly, even though that seems a bit redundant. We can now use scream loudly in a composition with repeat, pass it our string, and get the same result. The associative property allowed us to achieve the same results with each of these because we didn't change the order of operations, we only changed the grouping of the functions through subcompositions. Compositions of pure point-free functions can often be opaque and difficult to debug. Let me demonstrate that with an example. I'm going to create a function, slugify, that will take these book titles and turn them into URL slugs. I'm going to purposely put a bug in the code. Now, let's try logging out the result. We get a huge error. What we see is that string to lowercase is not a function, which probably means when we get to lowercase, the value getting passed in isn't a string. What we need is a function that gives us a side effect of being able to log out the current value. We can do this by creating a trace function. Trace receives a message as its first argument, and then the value getting passed to it. And now we're going to use the comma operator to log out our message and value and return the value. Now we can place traces before and after functions in our composition in order to see the value transform step by step. We'll place a trace before we split. Remember, with compositions, we work from right to left or bottom to up, hence why that one's before. We'll call this one after split. And finally, we'll put one after lowercase. We'll save this and run it in the terminal again. We still got our error, but now we can see a little more information about what's taken place. Before split, we have our array of book titles, and after split, we actually have a two-dimensional array. What happened was that split took our strings, split them at spaces, and made them arrays themselves. And our map lowercase isn't working because lowercase expects a string, and what it's getting is an array. What we can do is reverse the arguments that we have of map split and map lowercase. So now I'll rename my trace functions. I'll save it and I'll run it again. All right, we didn't get an error, but I didn't get slugs at the bottom either. Let's look at our trace one more time. Before lowercase, we have the array of titles like we had expected. After lowercase, we still have a one-dimensional array of lowercase strings. After the split, it looks like we now have a two-dimensional array. Each one was split at their space, and now we have each string individually. What happened when we called join on this array is we actually put the hyphen between the last and the first values of each array. What we need to do is we need to call a map on join as well. We'll come back to our code, we'll add map here, we'll save this, and we'll run our code again. And you can see we now have an array of slugs exactly like we expected. We can now clean up our traces, knowing that our function works the way we expected, save it, and run it. Nothing should have changed. We still have our array. Now you might notice we're calling map on all of these. So how could we make this better? Well, we can make a composition of the functions and pass it once into map. We'll save that, and we'll run it in our terminal, and we get the same answer.